Okay, section 3.7, other two-level implementations. Type of gates most found in integrated circuits are NAND and NOR gates. For this reason, NAND and NOR gate, NAND and NOR or logic implementations is the most important from a practical point of view. Some, but not all, NAND or NOR gates allow the possibility of a wire connection between the outputs of two gates to provide a specific logic function. This type of logic is called a wired logic. For example, open collector TTL NAND gates, when tied together, perform wired AND logic. Okay. That shows you on a wired AND in the open collector TTL NAND gates as an example. So you have your AND here, and then of course the NOT here. And then those are coming in wired in here. Now that's different than the other ones where see the AND gate is drawn with lines going through the center gate to distinguish it from a conventional gate. Our conventional gate was where it is coming in from the back here. So this is a different kind of design. And you see you use a different symbol here too. Now, got A, B plus C, D. Okay, so that's up to here. Okay, so we got our A, B coming in, inverted, C, D coming in, inverted, and then there's an AND between them. Now, there's nothing special about the AND. And so then at this point, using De Morgan's theorem, the multiplication becomes addition, and then we invert the AB and the CD. And they're already AB prime, so invert that gives you AB. And then here, De Morgan's theorem again, this is A times B, or A and B, so that becomes a plus, and we invert each one of those. So that's where the A prime plus B prime comes from. Here we got CD, or C and D, so the multiplication becomes addition, and then we invert each one of them. That's where the C prime plus D prime comes from. Which gives you this picture here. So we got our, which one is this? It's not that one. Okay, this just strictly has to do with this side over here. Okay, here's the one for the NOR. So again, this is our OR gate, so A plus B and the inverts on the front here. So that's why the A plus B is primed, plus C plus D primed, and there's a plus between them to handle this. And again, that's just a different, it's still an OR gate. It's just it's wired in. This spot talking about other forms, non-degenerate forms. It'll be instructive from a theoretical point of view to find out how many two-level combinations of gates are possible. We consider 4 types of gates, AND, OR, NAND, NOR. If we assign one type of gate for the first level and one type for the second level, we find there are 16 possible combinations. That's from the multiplication rule. We've got 2 levels, there's 4 possibilities on each one, 4 times 4 gives you 16. And 8 of these combinations said to be degenerate forms because they degenerate to a single operation. So you don't need to write them in a more complex form. This can be seen from a circuit with the AND gates at the first level and the AND gate in the second level. The output of the circuit is merely the AND function of all input variables. This gives you the non-degenerate forms here. Okay. This shows you some different examples. Here's the and or invert implementation. Two forms, NAND and NOR are equivalent, can be treated together, both perform the and or invert function, as in shown in 3.27. The and NOR resembles the and or, both inversion done by bubble and the output of the NOR gate. It implements this function. And or invert, or and NOR. Okay, so A and B are coming in. A times B, or A and B, C and D, E, all of them are coming in to an OR gate, that's plus, and then a prime is because of the little circle on the front there. We could give the breakdown to that. This one and this one are very similar. Here we have the and then we have our negation in the front of the OR. And this one takes these back to a NAND gate. Here you have to put E or start this as E prime, one of the two. If you start with E, you have to have your inverter gate because these have to come in that form. Let me write that out. I'll look at C just to show it. Because I haven't plugged in my tablet. Okay, so come into an and. You do have to have prime on the outside. Okay, I was drawing a blank there. So AB plus CD plus E and then prime. There's a prime in here going backwards. Morgan's tells us we can rewrite the addition, assuming you have prime here. We can rewrite as addition as multiplication, and we just have to prime each one of those. So this is the same thing as this over here. Okay. As this is the same thing too. Now the OR and invert implementation. The OR and 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 NOR OR forms form the OR and invert function. The OR and AND form resembles the OR AND form, except for the inversion done by a bubble in the NAND gate implements this function. A or B, C or D, E, coming in here, there's a multiplication, and then invert on front, which is a prime. And then here's an OR NAND implementation, and here's the B. Not feeling very good today, so I'll use that as an excuse. Oh, I see. They're saying by using the alternative graphic symbol for the NAND gate. We obtain the diagram of 3.28b. As I say, I don't see a NAND gate in there. See a NOR gate. But when it comes from the back, once that's our alternative. I'm not remembering. Okay. Those are NOR gates. That's an OR gate. Okay, I see that. These are OR gates. This is a NAND gate. I guess I don't see that on this one. Okay, so I'll pick on this one. This is A plus B and then a prime. And here's a C plus D and a prime. And then here's an E prime. I put plus between all those because this is an OR gate over here to the far right. Okay, so that's how they get that. Because I have to think of it kind of going backwards. If everything's prime here, the multiplication becomes addition, and you just have to prime each one separately. So going backwards, yeah, assuming they're all, well, they don't even have to be primed, I guess, because you're just gonna flip them. We got plus across the board, so we can rewrite as multiplication, invert in each one of these from wherever they were, and then putting a prime on the outside. Again, De Morgan's. This tells you if you want to use that particular implementation, what form do you need to put it into. And since these are just strictly from a theory standpoint, I'll let you read the rest of that. And let's go to 3.8. Exclusive OR function. This is denoted by this symbol. It looks like a plus with a circle around it. It's a logical operation performs the following Boolean operation. X and not Y, or X or not X and Y. So X, Y prime plus X prime Y. Exclusive OR is equal to 1 if and only if X is equal to 1, or if only Y is equal to 1. Basically, if X and Y different values. When both are equal to 1, but not when they're both equal to 1 or both equal to 0. Okay. Exclusive NOR also known as equivalence, performs the following Boolean operation. I just said that. Oh, this is the inverting it. Oh, exclusive NOR. Okay, read a little closer. So it looks exactly the same, except for we have to put the prime on there. That gives you xy plus x prime y prime. Trying to think why. Y prime plus x prime y. Yeah, if I wanted to invert that, well, the addition here becomes multiplication, and then I invert these, so that would be x y prime prime. That'd be x prime y prime. Then this is prime, so by De Morgan's, this multiplication here becomes addition. And I prime each one of these. So that'd be x prime plus y. This one's prime, so again, I prime those, and multiplication becomes addition. So x plus y prime. Because when I take x prime times x, that gives me x prime x, x prime times y prime, x prime y prime, x times or y times x, yx or xy, whatever, y times y prime, y prime. And this must have been equal to 0 from our properties, if I went to look. And that's why we're left with xy plus x prime y prime. Okay, that makes sense. Then they give you some identities. It goes to the exclusive OR operation. X XOR 0 is equal to X XOR 1 is equal to X prime, X XOR X is equal to 0, and that's equal to 1, and so forth. Any of these can be shown with the truth table. And they're implementing this with and or not gates. So X prime, Y, and y prime. Okay. Okay, so, oops, let's see, x, y prime, and another AND gate here, and x prime, y, and those are coming into an OR gate. So that's how you'd do the logic for the circuit. Now, exclusive OR with NAND gates. X, Y prime. X. Let's see, edit, paste. X and Y coming in. This X is coming in here. It's coming up like that. Okay, so X is coming in, this is coming in, this primed. This one, I have Y, and what's coming in here? Again, the same. Then they're coming into that. Oh, there should be an invert here. Okay. Then the invert here. And their claim is that gives you this original value here. Okay, so again, prime on the outside, and I got two things multiplied together. So that becomes addition, and I flip each one of these. So that's x, y primed, and that flips. Plus, this would be y, x, y primed, and that flips. Okay, so now what's inside here? Got this prime, so it becomes addition, And I prime each one of those, so that's x prime, y prime. Y carries down, again, same thing here, that becomes x prime, y prime, De Morgan's. I bet if I just multiply these together, that's where it gives you x prime plus x y prime plus x prime y plus y prime, y prime, and x prime drops away, and x y prime plus x prime. Yeah, sure enough, although I didn't do it very neat here, it should be an x. Okay, so just showing you the different ways you can implement the different types of gates. Drink here. The exclusive OR operation with three or more variables can be converted to an ordinary Boolean function by replacing the XOR symbol with its equivalent Boolean expression. In particular, the three variable case can be converted to a Boolean expression as follows. I see it. Because first, the A XOR B is the A B prime plus A prime B. It's inside the parentheses. And then the XOR the C, you just have to put a C prime on the end there and a C on the end there. And then use the distributive property, and then that gives you what the corresponding would be. Boolean expression clearly indicates that three variable exclusive OR function is equal to 1 if only one variable is equal to 1, or if all three variables are equal to 1. Contrary to the two variable case, in which only one variable must be equal to 1, in the case of three or more variables, the requirement is that an odd number of variables be equal to 1. As a consequence, a multiple variable exclusive OR operation is defined as an odd function. Okay. Talks about the three input odd functions implemented by means of the two input exclusive OR gates, as shown in figure 3.32a. The complement of an odd function is obtained by replacing the output gate with an exclusive NOR gate. That's with the little circle in the front there. Then it talks about the four variable case. Okay. Why even talk about exclusive OR? Parity generation checking. Exclusive OR functions are useful in systems requiring error detection and correction codes, as discussed in section 1.7. A parity bit is used for the purpose of detecting errors during transmission of binary information. Parity bit is an extra bit included with the binary message to make the number of ones either odd or even. The message, including parity bit, is transmitted and then checked on the receiving end for errors. An error is detected if the checked parity does not correspond with the one transmitted. Circuit generates a parity bit, and transmitter is called a parity generator, and circuit that checks a parity and the receiver is called a parity checker. Okay, so this one's an even parity, this example. So we've got our 3-bit message 0000 001. Since we only have 1 we need another one here just so it's an even number. And 2 1s, 2 1s, 2 1s, 2 1s, 2 1s, and down here, when all 3 of these are 1s, we need an additional 1, so it's 4 1s. So again, that's our even parity. Now here's how we can generate the parity bit. Well, where'd my history go to? Oh, should have this memorized, but I don't. There it is. X, Y prime. Plus X prime Y. So zero, zero, zero. One zero one zero one zero one. Okay. Now, if I looked at the X or Y, we have XY prime. And we also have X prime Y. Think this through. This would be 0 0 0 0 1 1 0 0. This one be 0 0 1 1 0 0 0 0. 0, 0, 1, 1, 1, 1, 0, 0. Okay, which makes sense because we said that anytime it's equal to 1 is when they're different. I was just showing that, but I got this now. And that's coming into this, and then I want to do that with Z. So I'm now working with this one. And that one. So the XOR between those would be where they're different. So that's a 0 there, 1 there, 1 there, 0, 1, 0, 0, 1. Now, if I count how many ones are here, there's 0 or 0, and so this is 0. This is our parity bit. 0, 0, 1, we have to add a 1, so it's 2. 0, 1, 0, we have to add a 1, so it's 2 of them. Here we already have 2, so I don't need any more, so I put a 0 there. Here I only have 1, 1, so I need another one for the parity bit, even parity. Here's 2, so I don't need any more. Here's 2, so I don't need any more. Here's 3, which is odd, which means I need another one, so that's where that is. I find it really interesting how they can implement various constructs using gates. That right there would end up giving you the parity bit. And this, if I were to go through the process, would give us our checker. Now, I wonder what C would gives us though. Okay, 3 bits in a message. The parity bit is transmitted to destination where they apply to the parity checker circuit to check for possible errors in transmission. Since the information is transmitted with even parity, the 4, I guess I could think of this. Let's see, X and Y, this would be when they're different. This would be when they're different. Never mind, I don't see it. Okay, a error occurs if a transmitted the 4 bits received have an odd number. The output of the parity checker denoted by C will be equal to 1 if an error occurs. Okay, so C will be turned 1. I'd have to actually run through to fully understand that, but okay. I guess it's obvious when it comes through. Will be equal to 1 if an error occurs. If you look at the table they've built for that, I won't go through and do it, but 0, 0, 0, parity is 0, we get a 0. 0, 0, 0, and then parity of 1, well, that right there has an odd number of ones, so it's got to be even. So that's why that's a 1 or an error. This is an error. This one, though, 0, 0, 1, and then a 1, that gives us our 0, meaning no error. Okay. Well, we're ready for the HTLs. So I think we'll stop there because I want to start in fresh on the programming on that. I'll show you how to use the software to do that. And it's another free package we can use to write the programs in and implement them. So we'll stop there.